A 2,000-year-old concrete dome still stands without a single steel beam. Modern bridges and buildings, engineered with our latest science, often show their age in just 50 years. This is not just a curiosity, it is a glaring clue that we have forgotten something vital. By the end of this exploration, you will understand the precise chemical and philosophical ingredients that made ancient structures virtually eternal. We will uncover why seawater made their harbors stronger and how a volcano's ash became the foundation of an empire. What does it say about our own civilization that we build things not to last, but to be replaced beneath the gentle Mediterranean waves lies a contradiction that defies modern engineering. A diver gliding over the submerged piers of an ancient Roman harbor is not exploring delicate ruins, but confronting structures as solid as the day they were poured. These blocks, resting on the seafloor for 2 millennia, have faced a constant, brutal assault from saltwater, a force that eats away at modern concrete in mere decades. Yet here, the stone seems to have grown only harder, more resilient with time. This is not a lucky accident. It is the signature of a forgotten technology, a specific formula the Romans called opus cementitium, designed from the ground up, or rather from the water down, to thrive in the very environment that destroys our own. The Romans did not just make concrete that could get wet, they engineered a hydraulic concrete, a material that actually required water to achieve its final, indestructible form. While we use Portland cement, a product of intense industrial heat, their magic ingredient was volcanic. They sourced a fine, glassy ash from the slopes of volcanoes, material we now call Pozzolana. When this ash was mixed with lime and chunks of rock aggregate, something extraordinary happened upon contact with seawater. A complex chemical conversation began, one that is still ongoing today. Materials scientists like Marie Jackson describe Roman maritime concrete not as an inert, dead slab, but as a reactive, almost living material. The salt water did not attack it. Instead, it permeated the mixture, slowly triggering new mineral growths within its microscopic pores. Consider the colossal harbor at Caesarea Maritima, built for King Herod the Great. Its concrete breakwaters were sunk directly into the turbulent sea. For over 2,000 years, every crashing wave has been a test. Modern concrete in that setting would have dissolved, the steel reinforcement inside rusting and expanding until the structure cracked apart. But the Roman concrete, with no steel to corrode, performed differently. The seawater percolating through it formed rare, plate-like crystals that interlocked, reinforcing the material from the inside out. The more the sea tried to wear it down, the more these durable minerals grew, creating a self-healing matrix. This reveals a profound philosophical divide in construction. We engineer for immediate, overwhelming strength, often at the cost of long-term resilience. The Romans engineered for time, creating a material that partnered with its environment, even one as hostile as the open sea. So what was the secret handshake between the volcanic ash and the ocean? The answer lies not just in the ingredients, but in a lost art of preparation we are only beginning to decipher. The true secret was not in the water, but in the fire that came before it. To understand Roman concrete, you must first understand the unique geology it demanded. Across the Bay of Naples from Pompeii lies the quiet town of Pozzolana, a place that gave its name to the foundational ingredient of an empire. Roman engineers did not simply use any dirt or sand. They sought out a specific, unassuming powder, a fine, brownish-gray ash harvested from the slopes of volcanoes like Vesuvius. This was Pozzolana, and it behaved like nothing else on Earth. In his architectural manual, the engineer Vitruvius wrote with clear intent about finding the ash that, when mixed with lime and rubble, not only hardens in ordinary structures, but also underwater. He was describing a chemical marriage, not just a recipe. The magic of Pozzolana lies in its microscopic structure. It is rich in reactive silica and alumina, compounds that are essentially locked in a glassy, amorphous state by the intense heat of a volcanic eruption. When this volcanic glass is mixed with slaked lime, which is calcium hydroxide, and then introduced to water, a slow, profound transformation begins. The water acts as a catalyst, allowing the silica in the ash to react with the lime. This pozzolanic reaction creates a dense, interlocking network of stable compounds, primarily calcium aluminosilicate hydrate. Think of it not as a glue that dries, but as a crystalline forest that grows, filling every pore and void, binding the aggregate into a single, monolithic stone. This is where Roman concrete diverges fundamentally from our own. Modern Portland cement, invented in the 19th century, produces a different binder, calcium silicate hydrate. While strong, it forms a more brittle gel that is susceptible to cracking over time, especially when attacked by chemicals like salt. The Roman compound, however, was more complex, more durable, and crucially, it thrived in the presence of moisture. The Romans were masterful geologists. They did not treat all ash as equal. They identified and categorized deposits from specific volcanoes, understanding through trial and observation that ash from the Alban Hills, for instance, was ideal for the load-bearing foundations of roads like the Appian Way, while the ash from Pozzuoli was reserved for their most critical maritime works. This raises a fascinating question. Did Vitruvius and his contemporaries understand the atomic dance of silica and alumina? Almost certainly not in the terms a chemist uses today. Their knowledge was deeply empirical, built over generations of observation. They knew that mixing this particular ash from that specific hill with lime and water produced a stone that could defy the sea. They knew the formula worked long before they knew precisely why. This volcanic foundation provided the reactive soul of the concrete, but it was inert powder without its activating partner. The ash alone could not harden. It required a key to unlock its latent power, a substance that would initiate the entire chemical symphony. That key was lime, and its production was an art form all its own. That volcanic ash was potent, but it was utterly inert without its reactive partner. To unlock its power, the Romans needed a substance born from fire. This was quicklime, the volatile heart of their concrete. Picture a landscape outside the city, where plumes of white smoke rise not from a house fire, but from a carefully constructed dome of stone and brick. This is a lime kiln, an industrial furnace of the ancient world. Workers feed it with pure white limestone, a rock composed of ancient sea creatures compressed over eons. For days, a roaring wood fire is maintained at a staggering heat, often exceeding 900 degrees Celsius. This intense, sustained fire does not simply warm the stone. It transforms it. The process, called calcination, drives off carbon dioxide, leaving behind a brittle, white substance. This is quicklime or calcium oxide, a material so chemically hungry and caustic it can burn skin on contact. Its creation was a dangerous, precise operation. Archaeologists studying Roman kiln sites find evidence of remarkable standardization. The kilns were built to specific dimensions to maintain consistent, high temperatures, and the limestone was carefully selected for purity. This was not a haphazard craft. It was a controlled chemical industry producing a key ingredient to a reliable specification. Now, here is where Roman practice diverges from modern logic and reveals a layer of their genius. Today, builders slake their quicklime immediately. They add water to it, creating a safe, putty-like paste of calcium hydroxide before it ever touches the mix. The Romans often did not. Evidence from sites like the markets of Trajan suggests they frequently used a hot mixing technique. they would take chunks of this reactive, unslaked quicklime and combine it directly with the volcanic ash and aggregate. When water was added to the entire mixture, two things happened simultaneously. The quicklime chunks began their violent reaction with the water, releasing tremendous heat, while the pozzolanic reaction with the ash began. This internal furnace created a unique curing environment. The heat accelerated chemical processes and likely helped form a more complex, interlocking crystalline structure throughout the concrete as it set. For a long time, modern researchers examining Roman concrete samples noticed strange, white, pebble-like inclusions scattered throughout. They were assumed to be mistakes, bits of unmixed lime, flaws in an otherwise good recipe. But advanced analysis has turned that assumption on its head. These lime clasts, as they are called, are now seen as a potential self-healing feature. The theory is compelling. When a tiny crack eventually forms in the ancient concrete, it propagates through the material until it hits one of these white lime clasts. Water seeps into the crack, reaching the untouched, reactive quicklime at the clast's core. This triggers a new, localized pozzolanic reaction. The crack fills with freshly formed calcium aluminosilicate hydrate, essentially healing itself from the inside. Was this intentional? It is difficult to say with absolute certainty, but the consistency of the clast's presence across major Roman projects suggests it was more than an accident. It points to a profound, embodied knowledge of their materials. The Romans understood that introducing this controlled chaos, this pocket of latent chemical energy, into the mix could yield long-term benefits they might never see, but their monuments would. So we have the volcanic ash and the fiery lime, two powerful ingredients waiting for their catalyst. Alone, they were just powder and rock. Together, with the final, simplest ingredient, they would begin a reaction meant to last for millennia. The final, simplest ingredient was all around them. For the great harbors at Portus or Caesarea, the mixing water was not drawn from a clean river or a well. It was hauled directly from the sea itself, briny and thick with dissolved salts. To a modern engineer, this would seem like sabotage, an invitation for catastrophic failure. For the Romans, it was the final, deliberate step in a chemical masterpiece. They understood that seawater was not a corrosive enemy to be kept out, but the essential catalyst that would trigger the concrete's ultimate strength. When the slurry of volcanic ash, hot lime, and aggregate met the saltwater, a slow miracle began. A reaction started that was designed not to finish in weeks, but to continue for centuries, transforming the material from within long after the builders had departed. Recent studies using advanced X-ray microscopy have allowed scientists to peer into the atomic heart of 2,000-year-old harbor samples. What they find is astonishing. Scattered throughout the concrete matrix are rare, plate-like crystals with complex names, altobermorite and philipsite. These are not relics of the original mix. They are newborn minerals, forged over time by the ongoing conversation between the salt ions in seawater and the reactive compounds in the ash and lime. Think of them as a microscopic reinforcement bar, but one grown organically by the material itself. These sturdy, interlocking crystals act like a geological armor. As tiny stresses form micro-cracks in the concrete, these cracks propagate until they hit a wall of these dense, plate-like crystals. The path is blocked. The damage cannot spread. This is the exact opposite of what happens in modern reinforced concrete. In our structures, salt water is a relentless infiltrator. It seeps into pores, reaches the steel rebar, and causes it to rust. That rust expands with tremendous force, bursting the concrete apart from the inside in a process called spalling. The Roman formula had no such weakness. It had no steel to corrode. Instead, the seawater it was mixed with became the agent of its eternal fortification. Core samples drilled from the ancient harbor of Portus, the great maritime hub of Imperial Rome, tell this story in stone. They are not crumbling relics. They are dense, coherent, and shot through with these beneficial crystalline formations. The material is actually stronger in the zones most exposed to seawater, a direct rebuke to everything we assume about durability. This forces a profound shift in perspective. We see time and environmental exposure as forces of degradation, enemies to be fought with sealants and repairs. Roman concrete suggests a different philosophy. What if the building process does not end when the last block is laid? What if a structure can be designed to continue its own construction, molecule by molecule, for generations, using the very elements that would destroy a lesser material? This crystalline growth is not passive. It hints at a latent, self-healing potential written into the recipe. A crack that lets in new seawater might not be a death sentence. It could be an invitation for the material to knit itself back together, to grow new mineral bridges across the fracture. It is a technology that embraces time as a partner. But if this knowledge was so powerful, so clearly effective, how could it simply vanish from the world for over 1,000 years? The answer lies not in a single cataclysm, but in a slow, quiet unraveling of an entire system of knowledge and trade. The chemical reaction was only half the story. A Roman construction site was a scene of organized chaos, where another critical selection process was underway. Workers sorted through piles of rock, not just for size but for type. This was the curation of the aggregate, the cementer, the rubble that formed the concrete's internal skeleton. It was far more than filler. Modern concrete often uses smooth, rounded river gravel chosen for its ease of mixing. Roman engineers sought the opposite. They preferred rough, angular fragments of volcanic rock, like tough or even crushed brick. Why? A jagged edge creates a vastly superior mechanical bond, locking the stone into the cementitious paste like 1,000 tiny interlocking hands. But the genius went deeper. These volcanic aggregates were not inert bystanders. They were chemically reactive participants. The porous tuff, rich in silica and alumina, could engage in a slow, long-term pozzolanic reaction with the lime-rich binder at their interface. This blurred the line between glue and stone, creating a monolithic material where every component was actively contributing to the whole. Vitruvius was explicit in his instructions. He warned against using dirty or dusty aggregate, as it would weaken the bond. He detailed the importance of gradation, the careful mix of different stone sizes from fist-sized chunks down to coarse sand. This was the key to minimizing voids. Imagine filling a jar with only large marbles. You will see many gaps. Now add smaller pebbles to fill those spaces, then sand to fill the tinier gaps. The Romans were masters of this packing principle. Their mix resulted in a densely interlocked matrix, leaving little room for the pores and weaknesses that plague modern concrete. This physical artistry directly contributed to legendary durability. Look to the foundations of the Colosseum, a structure that has borne immense weight and seismic shifts for nearly 2,000 years. Engineers there used a strategic blend of heavy travertine limestone and lighter, cushioning tuff. This was not a random choice. It distributed loads intelligently and provided a degree of flexibility, a shock absorption built right into the stone. Sustainability was an embedded practice, not a modern add-on. Archaeologists frequently find fragments of crushed pottery and tile mixed into Roman concrete. This recycled material, known as coxiopsto, was more than economical. Broken ceramics are rich in alumina, which further enhanced the chemical complexity and strength of the binder. It was a closed-loop system, turning waste into a building material of exceptional quality. So we must ask, how much of this ancient concrete's legendary strength was chemistry, and how much was this physical, almost artistic assembly? The answer is both, inseparably. The reactive volcanic aggregate and the graded, angular rubble created a physical fortress. The pozzolanic ash and hot lime mix provided a chemical binder that could infiltrate and fortify that fortress over centuries. One without the other would not have achieved the same result. With the volcanic ash, the fiery lime, the saltwater catalyst, and now this meticulously curated aggregate, the formula was complete in the bowl. But a recipe alone does not bake a cake. The potential of this near-magical mix now rested entirely in the hands of the builders, in the final, human element that would determine its fate, craftsmanship. The final formula was only as strong as the hands that placed it. On a Roman construction site, the mixing of concrete was a deliberate, rhythmic ceremony. Teams worked in coordinated sequence, combining precise volumes of volcanic ash, hot lime, and graded aggregate in wooden troughs. Water, often seawater for harbor works, was added not all at once, but in stages as the mixture was turned and folded by hand or with long paddles. This was not about speed. It was about achieving a perfect, uniform consistency, a thick, cohesive mortar that would hold its shape when molded. The goal was to eliminate any dry pockets or weak zones before a single load was ever poured. Experimental archaeologists attempting to replicate the process today speak of the surprising physicality and patience required. The timing was everything, especially for underwater works. For structures like harbor piers, the Romans employed an early form of the tremie method. They would lower prefabricated wooden forms into the water, then use a long tube or chute to funnel the wet concrete directly to the seafloor, displacing the water as it flowed. This prevented the mix from washing away and ensured it settled densely without segregating into layers of heavy rock and weak slurry. Once in the formwork, the real artistry began. Workers did not simply dump it and leave. They used wooden poles to rod and tamp the material vigorously, driving out trapped air bubbles. This manual compaction was grueling, repetitive labor, but it was essential. It forced the paste to fully envelop every piece of aggregate, creating a homogeneous, low-porosity mass with virtually no weak planes. Modern concrete is often poured in vast, continuous operations. While efficient, this can lead to thermal stress and shrinkage as it cures, creating microcracks from the very beginning. The Roman approach of placing in smaller, carefully managed layers mitigated this. Each layer could partially set and stabilize before the next was added, reducing internal stress and creating a more monolithic, unified structure. Some researchers speculate that organic additives, like animal fat or even blood, might have been used as plasticizers to improve workability, though evidence remains debated. Whether true or not, it highlights their experimental, holistic approach to material science. The ultimate testament to this craftsmanship is overhead. Look at the Pantheon's dome, a perfect hemisphere of unreinforced concrete that has defied gravity for 1900 years. Its construction was a masterclass in intentional variation. At the thick, supporting base, the aggregate is heavy basalt. As the dome curves upward, the mix changes. Lighter materials like tuff and brick are introduced, and at the very top, surrounding the oculus, the aggregate is porous pumice. The builders were literally lightening the load as they climbed, tailoring the concrete's density and weight with breathtaking precision. This was not a one-size-fits-all material. It was a responsive medium sculpted by understanding. So we must ask, in our pursuit of speed and scale, have we sacrificed the deep, embodied art of building for the detached science of manufacturing? The Roman craftsman knew his mix by feel, understood its setting time by sight, and trusted the tamping of his rod to the future. That meticulous, human care in placement was the final, invisible ingredient that locked the chemical potential into eternal stone. A hairline fracture thinner than a human hair appears in a 2,000-year-old wall. In any modern structure, this tiny flaw would be a death sentence, the beginning of a slow, inevitable failure. But in Roman concrete, it is the start of a repair process we are only now learning to see. deep within that microscopic crack, something astonishing happens. Over decades, a new mineral begins to form, a white, crystalline deposit that slowly fills the gap from the inside out, sealing the wound shut as if it were never there. This is not science fiction. It is the self-healing phenomenon of ancient concrete, a passive, automatic repair system built into the very chemistry of the material. Modern researchers using electron microscopes have watched this process in action. The secret lies in those white lime clasts we discussed earlier, the little pockets of reactive quicklime deliberately left unmixed. When water, even rainwater, seeps into a new crack, it eventually reaches one of these clasts. That water dissolves a tiny amount of the highly reactive calcium oxide, creating a solution super-saturated with calcium ions. This solution then flows back into the crack. There, it reacts with carbon dioxide from the air, precipitating out as a new layer of sturdy calcium carbonate, the same mineral that makes up limestone and marble. It is nature's own glue, manufactured on site by the concrete itself. Teams from MIT and Harvard have documented this process in exquisite detail. They note that the pozzolanic ash, which continues its slow reaction for centuries, acts as a long-term reservoir of reactive silica, further fueling this regenerative cycle. This means the material does not merely resist damage, it actively responds to it. A crack is not just a flaw, it is a trigger for new growth. Consider the concrete of the tomb of Caecilia Metella, a massive cylindrical monument on the Appian Way. Scientific analysis reveals not a pristine, unbroken stone, but a material with a history of tiny fractures. Crucially, those fractures show clear, layered mineral deposits within them, like geological scar tissue. This is evidence of multiple healing events over its long life, each one a silent testament to the concrete's embedded resilience. Contrast this with our modern approach. When a bridge deck or parking garage cracks, we engage in a costly, disruptive, and often temporary repair cycle. We patch it from the outside, an external fix that does not address the internal cause. The Roman method was fundamentally different. They engineered a material that could patch itself from within forever. This forces us to rethink the very goal of engineering. We strive for materials that are inert and stable, that resist change. But what if the highest form of durability is not passive resistance, but active regeneration? Can we learn to build things that are not just strong, but alive in their capacity to heal? This self-healing property was likely an observed benefit rather than a consciously designed feature. The Roman builders knew their hot mixed concrete with its lime chunks produced a superior, longer-lasting stone. They may not have visualized the microscopic repair process, but their empirical mastery led them directly to it. Their philosophy was not to build for 100 years, but to build for always. This intrinsic drive for permanence stands in stark contrast to our own disposable mindset. So we have uncovered the ingredients, the mixing, and even the self-repair. But such a powerful, empire-spanning technology could not have been the work of a single brilliant mind. It required an entire system of knowledge, a vast and living network that connected the quarry to the kiln to the construction site. When that network collapsed, the formula did not just fade, it shattered into disconnected fragments, lost for over a millennium. Steam would have risen from the mixing troughs on a major Roman work site, a visible sign of a hidden power source within the material itself. This is the heart of a compelling modern controversy, the theory of hot mixing. For decades, those white, pebble-like lime clasts found in ancient concrete were written off as evidence of poor mixing, a primitive mistake. A radical new interpretation suggests they were the engine of a deliberate thermal process. The idea is this: instead of slaking their quicklime into a paste beforehand, Roman builders often added chunks of it directly into the dry mix of volcanic ash and aggregate. When water hit those chunks, the reaction was immediate and violent. Quicklime combining with water is intensely exothermic, releasing a surge of heat. This was not a flaw to be controlled, but a furnace to be harnessed. The entire batch would warm significantly, creating an internal curing environment that modern lab mixtures, mixed cold, never experience. So what did this heat actually do? Advanced materials science provides a fascinating answer. The high temperature during the initial hours and days of curing appears to have accelerated the pozzolanic reaction dramatically. It also likely fostered the formation of a more complex, disordered nanostructure within the binding gel, the calcium aluminosilicate hydrate. Think of it like the difference between slowly cooling glass and rapidly quenching it. The hot mix process may have created a gel with a less orderly, more resilient architecture, one better at distributing stress and resisting the propagation of cracks. This nanoscale advantage translated to macroscale durability. The rapid heat also helped drive out excess water quickly, reducing the final porosity of the concrete from the very beginning. For massive projects like harbor moles or aqueduct foundations, which needed to bear load as soon as possible, this was a critical benefit. It meant the concrete achieved high initial strength rapidly, allowing construction to proceed without long delays. The thermal energy essentially acted as a catalyst, optimizing the microstructure for long-term performance. Skeptics rightly point out that proving this was intentional is difficult. We cannot ask Vitruvius about his understanding of exothermic chemistry, yet evidence is mounting through modern replication. Research teams have now mixed Roman-style concrete using both hot and cold methods, then subjected the samples to the same test. The hot mixed replicas consistently show superior fracture toughness. They do not just resist cracking, they blunt it. When a crack forms, it encounters a more tortuous path through the disordered gel and is often halted by the reactive lime clasts, which act as both healing agents and structural obstacles. This brings us to a reflective question. Were the Roman engineers then master chemists who understood the principles of thermal activation? Or were they simply brilliant empiricists whose generations of careful observation taught them that concrete mixed this way, with its steaming, lively reaction, simply produced a better, longer-lasting stone? The answer likely lies in the space between. They perfected a practice whose full scientific explanation would wait 2 millennia. The heat was not an isolated trick. It was one integrated element in a holistic philosophy, where every ingredient and every step, from the volcano to the kiln to the steaming trough, was part of a single, unified system aimed at one goal: permanence. But a system this sophisticated does not exist in a vacuum. It requires an empire to support it, a vast and living network of knowledge, trade, and logistics that stretched from Spain to Syria. When that network frayed, the recipe did not merely fade from memory. It became functionally impossible to execute. Silicon and oxygen get all the credit, but the secret handshake inside Roman concrete was performed by aluminum. Deep within the molecular scaffolding of that ancient binding gel, atoms of alumina carried in from the volcanic ash were the quiet architects of cohesion. While silica provides the backbone, alumina acts as a kind of chemical crosslink, bridging chains and creating the more complex, stable compound we call calcium aluminosilicate hydrate. This CaSH gel is the true hero, a nanostructure far more resistant to chemical attack and physical stress than the simpler calcium silicate hydrate found in modern mixes. Geochemists analyzing samples note with admiration that the specific volcanic deposits the Romans favored, like those from Pozzolana, were not just rich in reactive silica. They were perfectly, naturally balanced with alumina. This was either a stroke of immense geological luck or the result of generations of empirical selection, a slow refinement toward the ideal volcanic recipe. The presence of alumina fundamentally changes the gel's morphology. Instead of forming orderly, brittle crystals, it promotes a more disordered, gel-like nanostructure. Think of it as the difference between a sheet of glass and a dense sponge. The glass, while hard, shatters under a sharp blow. The sponge can compress, absorb energy, and rebound. This nanoscale sponginess allowed Roman concrete to accommodate stress, to flex minutely under load or seismic shift without developing the catastrophic cracks that plague more rigid materials. This introduces a fascinating paradox. In modern Portland cement production, alumina is often viewed with caution. If present in the wrong forms or proportions, it can lead to delayed setting or long-term instability. The Romans, using their natural volcanic ash, never faced this problem. The alumina was already locked in an ideal, glassy state, and their use of abundant lime naturally balanced the chemistry. The lime provided ample calcium ions to satisfy both the silica and the alumina, creating that robust, interlocking C/SH gel in perfect proportion. Evidence of this deliberate balance is etched in stone across the empire. Take mortar samples from the Aqua Traiana, an aqueduct that brought water to ancient Rome. Advanced spectroscopic analysis reveals not random variation, but a consistent alumina to silica ratio across miles of construction. This consistency speaks to a standardized sourcing and mixing practice, a controlled recipe that understood, on some level, that this ratio produced the desired result. It forces us to reflect how many of a material's legendary properties depend not on one or two superstar ingredients, but on the subtle, symphonic balance of a dozen elements. Roman concrete was not a simple recipe of ash and lime. It was a precise geochemical event, one where the local volcanoes of Italy provided a natural, pre-mixed formula that human ingenuity learned to activate. The concrete's strength was literally baked into the landscape, a partnership between earth and engineer that we severed when we moved to industrialized, uniform powders. This inherent link to place raises a haunting question. When the networks that supplied those specific volcanic ashes collapsed, did the knowledge become not just forgotten, but impossible to replicate elsewhere? The empire's strength was literally mixed from the soil of its provinces. If you mapped the Roman world not by its legions or emperors, but by its concrete, you would see a stunning mosaic of localized recipes. There was no single, universal secret formula locked in a vault in Rome. Instead, the true genius was a principle, a method of hyper-local adaptation that turned every territory's geology into a blueprint. Roman engineers were masterful empiricists, possessing a deep, practical knowledge of materials that allowed them to achieve the same legendary durability from wildly different ingredients. In the heart of Italy, they had the perfect volcanic ash from Pozzolana. But what did you do when building a fortress on the misty frontier of Britain, or a granary in the deserts of Egypt, 1,000 miles from the nearest volcano? You experimented, you tested, you substituted. Archaeological petrography, the study of ancient stone under the microscope, reveals distinct families of Roman concrete across the empire. In regions lacking good volcanic ash, engineers found a brilliant alternative: crushed terracotta or broken pottery and tile. This material, rich in alumina and silica from its initial firing in a kiln, behaved remarkably like Pozzolana. When mixed with lime, it produced a strong hydraulic mortar perfectly suited for baths, cisterns, and foundations far from the Mediterranean. Look to the eastern provinces, where builders used Santorini earth, a volcanic material from the Aegean, or further north in Germania, where a rock called trass was quarried and crushed for the same purpose. Each locale developed its own signature mix, a dialogue between Roman engineering standards and local geology. This adaptability created a remarkably sustainable, low transport cost model. Why haul tons of ash across mountain ranges when a suitable reactive material could be found nearby? The ultimate example of this geographical intelligence wins across the hills of northern England. Hadrian's Wall, a 73-mile-long barrier marking the empire's northern limit, is a masterclass in local sourcing. Analysis of its mortar and concrete reveals that its composition changed systematically along its length. Builders used whatever durable aggregate was close at hand, binding it with lime, and whatever pozzolanic material they could source or simulate locally. One section might use crushed granite, another local limestone, yet all were engineered to withstand the harsh, wet climate. This was not a compromise in quality. It was the height of practical intelligence, ensuring resilience by working with the landscape, not against it. It forces us to ask a profound question about our own world. In our drive for globalized, standardized materials, have we forgotten how to build intelligently with what lies beneath our feet? We ship Portland cement, a one-size-fits-all powder, across oceans, while ignoring the unique, reactive materials that every region offers. The Romans had no universal standard, yet they achieved universal durability through localized understanding. This very adaptability, however, sowed the seeds of the formula's eventual disappearance. When the intricate networks of knowledge and trade that supported this empirical system fractured, the principle was lost, leaving behind only the silent, varied stones. Their longevity was a testament to a forgotten way of thinking, one where a builder's most important tool was not a trowel, but a deep curiosity about the very ground he stood upon. Magnify a fragment of Roman concrete 1,000,000 times, and you do not find a simple, uniform stone. You enter a tangled, thriving forest. This is the nanoscale realm, where the material's true immortality is written. Here, the binding gel, calcium aluminosilicate hydrate, does not form neat, crystalline rows like soldiers. Instead, it grows in a dense, chaotic thicket of interlocking plates and fibers, a microscopic wilderness that is incredibly resilient. Modern Portland cement, by contrast, tends to produce a more orderly but also more brittle crystalline structure at this scale. Think of it as the difference between a pane of glass and a piece of tough, fibrous leather. The glass is hard, but a sharp impact causes a clean, catastrophic break. The leather can absorb the blow, distribute the force through its complex fibers, and remain intact. This disordered nano-architecture is the first secret of Roman concrete's toughness. It creates countless, tiny deflections for stress, preventing a single crack from finding a straight path to failure. Materials scientists using electron microscopes describe this gel not as a dead filler, but as a reactive, evolving ecosystem. The pozzolanic reaction between the volcanic ash and lime is not a one-month event. It is a process that continues at a glacial pace for centuries. As it proceeds, it deposits new gel into the tiniest of spaces, the nanopores within the concrete. Over decades, this slowly increases the material's density from the inside out, making it progressively less permeable and more solid. It is a building that continues to condense and strengthen long after its architects are gone. The most critical frontier in any concrete is the interface zone, the thin boundary where the cement paste meets the surface of a piece of aggregate. In modern concrete, this zone is often a weak link. It can be more porous, a fragile plane where cracks easily initiate and propagate. Roman concrete turns this weakness into a strength. The reactive volcanic aggregate and the lime-rich paste engage in a prolonged chemical handshake at this boundary. New minerals grow, bridging the gap and creating a seamless, chemically bonded transition from paste to stone. The aggregate is not just glued in, it is woven into the fabric of the gel. The evidence is visually stunning when placed side by side. Scanning electron microscope images of 2,000-year-old harbor concrete show a dense, interlocked matrix where it is difficult to tell where the binder ends and the aggregate begins. An image of modern marine concrete after similar salt exposure often reveals a different story, a landscape of microcracks, porous zones, and a clear separation at that critical interface. the early stages of a breakdown the Roman sample has resisted for millennia. This raises a profound design question for our own time. We value uniformity, predictability, and speed. Our industrial processes are engineered to eliminate variation, to create consistent, homogeneous materials. But what if the ultimate strength lies in engineered complexity, in a design disorder that mimics nature's own resilient structures? The Roman nanoforest was not created quickly. It was the product of a slow chemical conversation, one that required a formula and a mindset willing to invest in time we no longer possess. This intricate internal world was the final, invisible masterpiece, but even a masterpiece needs protection. If the concrete itself was so perfect, why did the majestic structures it built still require the careful, strategic planning of the architects who shaped it? A modern construction crew celebrates a milestone 28 days after a pour. Core samples are drilled, crushed in a press, and the concrete is declared to have achieved its design strength. The project is on schedule, the engineers are satisfied, and the building moves to its next phase. This 28-day mark is a sacred number in contemporary construction, a point where we consider the material's work complete. For the Romans, 28 days would have been merely the opening sentence of a story meant to span millennia. Our entire philosophy of material maturity is built on a different scale of time, one prioritized for economics over eternity. Modern building codes demand rapid strength gain. The faster a floor slab can bear weight, the quicker the next story can be built, the sooner the investment yields a return. This drive for speed shapes the chemistry of our concrete from the outset. To achieve high early strength, we use finely ground cement that reacts violently with water, releasing intense heat in a process called the heat of hydration. That heat is not a benign byproduct. In a massive pour, the interior of the concrete can become scorching hot while the surface cools rapidly. This thermal differential creates internal stress, leading to a network of microscopic shrinkage cracks before the structure ever bears a load. These tiny flaws are not considered failures. They are accepted as an inevitable cost of doing business quickly. They become the hidden pathways for future problems, the entry points for water and salts that will slowly degrade the material from within. The Roman approach was fundamentally different. Their concrete was not designed for a 28-day test. It was engineered as a slow geologic process, a deliberate transformation from a plastic mix into an artificial rock through continuous, low-level chemical evolution. The hot mixing technique, rather than causing damaging thermal stress, provided a controlled, pervasive warmth that optimized the initial cure without creating the same brittle, crack-prone microstructure. More importantly, the Pozzolanic reaction between the ash and lime was not a sprint. It was a marathon with no finish line. Studies of cores from the markets of Trajan or the piers at Portus show that reactive silica and alumina are still present, and new calcium aluminosilicate hydrate crystals can still be forming in pore spaces today. The concrete has been quietly strengthening, densifying, and healing itself for 2,000 years. What we call aging and degradation, their formula treated as a continuation of the curing process. This raises a pivotal question for our own time. What if our building codes valued the 100-year strength as much as the 28-day strength? What economic and cultural shifts would be required to build for the slow, steady gain of resilience over centuries instead of the rapid return on investment? Our accelerated methods can trap water within the concrete, leading to the formation of weaker, more expansive crystalline forms that compromise long-term integrity. The Roman formula, by contrast, seemed to encourage the growth of the stable, plate-like minerals that act as permanent reinforcement. The ongoing core sampling of ancient structures is not just an archaeological exercise, it is a stark lesson in material science. Each drill bit that extracts a cylinder of 2,000-year-old concrete is retrieving a data point in a 2 millennia-long experiment. The material is not a relic, it is a participant, still slowly reacting, still silently curing. This long-term view was not an accident of chemistry. It was embedded in a culture that saw its public works as legacies for unborn generations, as testaments to an eternal Rome. They built aqueducts, harbors, and temples not for a quick profit but for a perpetual future. In our race against the clock, have we forgotten how to build in partnership with time itself? This cultural divergence points to the ultimate reason the formula vanished. It was not merely a technical recipe that was lost, but an entire worldview about the purpose of construction, a philosophy that became incompatible with a world fracturing into a much shorter, more uncertain future. A modern cement plant is a monument to fossilized energy. Its central kiln, a colossal rotating steel tube, must maintain a continuous inferno exceeding 1,400 degrees Celsius, often for days on end, just to produce the basic powder we call clinker. The carbon dioxide bill for this process is staggering, accounting for roughly 8% of all human-made emissions globally. Now, step back 2,000 years. A Roman lime kiln was a simpler, quieter affair, a stone or brick dome where limestone was baked at roughly 900 degrees. The fuel was wood or charcoal, renewable for the time, and the temperature, while still high, was dramatically lower. This single difference in thermal ambition reveals a chasm in ecological thinking. The embodied energy, the total energy consumed from quarry to finished material, in Roman concrete was a fraction of our own. Their volcanic ash required no fiery transformation. It was mined, crushed, and used as nature provided it, a ready-made reactive powder. Their lime, while energy-intensive for its era, was produced at a scale and temperature that seems almost modest by comparison. Today, the most progressive green construction advocates point directly to this ancient model. They champion the use of supplementary cementitious materials, often called SCMS, like fly ash from coal plants or slag from steel production. These industrial byproducts are modern pozzolans. When they replace a portion of Portland cement in a mix, they not only reduce the carbon footprint, but often improve the concrete's long-term durability and chemical resistance. The Romans were doing this instinctively, using the natural byproduct of volcanoes to create a superior, low-energy material. Consider the full life cycle. A cubic meter of modern structural concrete, with its high Portland cement content and embedded steel rebar, can carry a carbon debt of several hundred kilograms. Estimates for its Roman equivalent, while difficult to pin down precisely, suggest a figure many times smaller due to the lower calcination temperature, the lack of fossil fuels, and the use of that natural, unprocessed ash. But the sustainability lesson goes beyond just production. Their concrete's legendary longevity is itself a profound form of environmental efficiency. A harbor that needs no repair or replacement for 2 millennia represents an immense saving of energy, labor, and materials across centuries. It eliminates the recurring carbon pulses of demolition, reconstruction, and transport that haunt our infrastructure cycles. Furthermore, by designing a material that needed no steel reinforcement, they avoided the entire spectrum of corrosion-related failures. Modern concrete's greatest weakness is often the steel inside it, rusting and expanding, dooming the structure to a finite lifespan. The Roman formula created a monolithic stone that could stand alone, its durability inherent, not borrowed from a metal that would eventually betray it. This ecological wisdom was likely a byproduct of necessity, not a conscious design for sustainability. They used what they had, and they used it wisely, building for permanence in a world without cheap energy. For us, the lesson is urgent and direct. In an age defined by climate consequence, can we afford to ignore a proven model of low-carbon, hyper-durable construction? The answer seems written in the very stones they left behind. monuments not just to empire, but to a forgotten harmony between human ambition and the limits of the physical world. Their success poses a silent, monumental question about our own priorities. The Pantheon's dome floats without a single internal skeleton. This is the most radical departure from our modern building philosophy, the fifth and perhaps most profound component of their concrete, a deliberate non-component, the complete absence of steel reinforcement. Roman architects and engineers faced the same physical laws of gravity and load, but they solved the equation with a different set of tools. Without the tensile strength of embedded metal rebar to resist pulling forces, they turned entirely to the power of compression and the genius of geometry. Their concrete was not a thin skin stretched over a metal frame. It was a massive, monolithic stone shaped to channel every force safely down to the earth. This required a masterful understanding of form. Look at any Roman aqueduct. Its repetitive arches are a lesson in pure compression. Each arch is a collection of wedge-shaped blocks, or in concrete, a shaped mass where gravity presses the elements tighter together, locking them into an incredibly stable curve. The downward weight is transformed into an outward thrust, which is then captured and countered by the immense mass of the piers. The entire structure works in a state of balanced, compressive equilibrium. Structural engineers studying the baths of Caracalla are not just looking at ruins, they are analyzing a masterclass in load distribution. The sprawling complex of vaults and domes was not random. The thickness of the walls, the curvature of the ceilings, the strategic placement of heavier materials at the base and lighter ones at the top, all formed a coherent three-dimensional puzzle where every piece carried its share of the load through compression alone. The absence of steel eliminates the single greatest failure mechanism of modern concrete, corrosion-induced spalling. In our structures, when water and salt penetrate the porous concrete and reach the rebar, the metal rusts. That rust occupies more volume than the original steel, creating tremendous internal pressure that cracks the concrete from within, exposing more rebar to the elements in a vicious, accelerating cycle of decay. Roman concrete had no such Trojan horse. Its durability was inherent, not borrowed. It could get wet, it could even develop hairline cracks, but without an internal metal component to corrode and expand, those flaws rarely led to catastrophic, progressive failure. This is not to say they ignored tension entirely. In some vaults, you find layers of flat bricks or terracotta tiles embedded within the concrete pour. These acted as a kind of light, capillary break and provided a modest amount of tensile reinforcement, but they were secondary, a subtle assist to the primary compressive system. They were not the structural backbone, they were more like the fibrous tendons within a massive muscle. The contrast in legacy is stark. Drive beneath a concrete highway overpass built in the 1960s, and you will likely see stained, patched surfaces and rust streaks bleeding from within, signs of a relentless, losing battle. Then stand beneath the soaring, coffered ceiling of the Basilica of Maxentius, constructed 1700 years earlier. Its concrete vault, though partially collapsed, shows no such internal betrayal. The stone itself has weathered, but it has not exploded from within by its own hidden weakness. This forces a difficult reflection. Did our brilliant invention of reinforced concrete, which allowed for the slender skyscrapers and vast cantilevers of the modern age, also create a cycle of dependency and planned obsolescence? We gained unimaginable freedom of form and incredible speed of construction, but we traded it for a material with a built-in expiration date, one perpetually at war with itself. Building without steel required a deeper, more intimate dialogue with the material and the forces it would face. It demanded that strength emerge from shape and mass, not from an implanted metal skeleton. This philosophy of monolithic permanence, however, could not survive the fragmentation of the world that created it. When the intricate, empire-wide system of knowledge and logistical support began to fray, the very mindset needed to execute such ambitious, long-term projects began to vanish. The concrete recipes did not just become forgotten texts. The culture of building for eternity faded into one of building for survival. A master builder in a Roman workshop never saw a chemical formula. His knowledge was not written in equations, but in the feel of the mix between his fingers, the sound of the aggregate as it was tamped, and the color of the steam rising from the trough. This was empirical mastery, a deep, holistic understanding passed from mentor to apprentice over generations within the collegia, the builders' guilds. They knew that ash from this particular hillside, mixed with lime burned for exactly this long, produced a mortar that could set underwater. They possessed the recipe, but more importantly, they possessed the craft, the tacit knowledge of 1,000 subtle variables that were never written down. Vitruvius's great architectural manual gives us the ingredients, but it cannot convey the rhythm of the rotting, the judgment of moisture by eye, or the instinct for when the heat of the mix was just right. This knowledge lived in the hands and the eyes of the craftsmen, in the collective memory of a continuous tradition. When that tradition was broken, the living art vanished, leaving behind only the silent, cryptic list of components. The modern materials laboratory operates on a fundamentally different principle, one of scientific reductionism. Here, the goal is to isolate, to purify, to understand each variable in isolation. We break concrete down into its constituent chemicals, calcium oxide, silicon dioxide, aluminum oxide, and we seek to optimize each one. We developed Portland cement by isolating and maximizing tricalcium silicate, known as C3S, for its ability to deliver high early strength. This focus on a single, dominant variable is powerful. It gives us control, predictability, and allows for mass production to a precise standard. But in this process of reduction, something can be lost. We may optimize for one property, like 28-day compressive strength, while inadvertently sacrificing others, like long-term chemical resilience or the capacity for self-healing. The Roman formula was not an optimized single variable. It was a synergistic system where the imperfections were features. The slightly variable composition of the volcanic ash, the chunks of hot lime, the rough, angular aggregate, all work together in a complex interplay that we are only now beginning to map with our most advanced tools. Early modern attempts to resurrect Roman concrete often failed spectacularly precisely because of this gap. Engineers of the 18th and 19th centuries, armed with Vitruvius's written recipe but none of the guild's embodied knowledge, produced weak, crumbly imitations. They had the words, but they had lost the music. They mixed the ingredients cold, they used smooth aggregate, they slaked their lime first, missing the entire thermal and textural philosophy of the process. This reveals an epistemological chasm, a difference in how knowledge itself was built and held. Roman engineering wisdom was cumulative, practical, and deeply contextual. Ours is analytical, theoretical, and seeks universal laws. One is not inherently superior to the other, but the loss of the former left a hole in our understanding of durability. This raises a pivotal question for our own era of advanced material science. Can we now achieve a synthesis? Can we use our powerful tools of molecular analysis and computational modeling not to replace that ancient empirical wisdom, but to finally decode it, to understand the why behind the what that the Roman builders knew so well? The goal would not be to simply copy an ancient recipe, but to grasp the underlying principles of synergy and time, and then design new materials informed by that deep wisdom. The hardest formula to rediscover may not be written in any ash or lime. It is the formula for a mindset, one that values the slow, observed truth of the workshop as much as the rapid, precise truth of the laboratory. The Pantheon's dome is not a single, uniform shell of stone. It is a vertical recipe book, its layers reading like the rings of an ancient tree, each one a deliberate choice in density and composition. To understand the lost formula fully, you must look upward through the very fabric of this 2,000-year-old ceiling. At the massive supporting ring, the concrete is thick and heavy, packed with dense travertine limestone and hard brick as aggregate. This foundation needed to anchor the entire structure, to bear the immense compressive forces pushing downward and outward. But as your eye travels up the gentle curve, the recipe changes. The aggregate lightens, shifting to porous volcanic tuff, and then, near the very top surrounding the great oculus, to the lightest material of all, airy pumice. This was not a matter of convenience or running out of heavy rock. It was a masterstroke of material engineering, a calculated gradation to reduce the dome's dead load as it soared. The builders were literally sculpting with weight, removing mass where it was least needed to prevent the structure from collapsing under its own heft. Recent architectural analysis and core samples have decoded this vertical stratification with stunning clarity. Computer models simulating the dome's stress distribution show a beautiful alignment with the physical evidence. The areas of highest compressive stress around the base correspond perfectly to the zones of the heaviest, strongest concrete. The models reveal that the famous coffered panels carved into the ceiling are far more than decorative. Each indentation strategically removes cubic meters of unnecessary weight without sacrificing structural integrity, like the careful hollows in a bone. The central oculus itself is not just a source of celestial light. It is a brilliant stress reliever, acting as the keystone of a perfect compression ring, eliminating what would have been the heaviest and most unstable point at the apex. Every element of the design works in concert with the tailored concrete. The Pozzolana that binds this masterpiece together was almost certainly sourced from local deposits, likely from the Alban Hills volcanoes just southeast of Rome. This specific ash, mixed with lime from kilns burning nearby limestone, created a reactive paste that infiltrated every jagged piece of the graded aggregate, from the travertine at the bottom to the pumice at the top. The chemical bond at each interface, that critical zone where paste meets stone, would have been as strong in the lightweight upper sections as in the dense lower ones, thanks to the ongoing pozzolanic reaction. This ensured the entire dome behaved as a single, monolithic entity. Was the Pantheon the pinnacle of a millennium of concrete experimentation? It certainly stands as its ultimate testament, a structure where every principle we have uncovered, the reactive volcanic ash, the hot mixed lime, the curated aggregate, the compressive geometry converged in one breathtaking act of architectural confidence. It represents a moment where empirical knowledge and ambitious vision achieved a perfect, silent balance, a recipe executed on a scale never truly repeated. Its enduring presence asks us what we might build if we combined our analytical power with that same reverence for time and material. The dome of the Hagia Sophia in Constantinople is a marvel of engineering, but its construction in the 6th century marks a subtle turning point in our story. While its architects achieved breathtaking spans and luminous interiors, they did so with a different approach than their Roman forebears. The structure relies on brilliant brickwork and mortar, not the massive, monolithic concrete pours of the Pantheon. This shift is the first clue to a slow, centuries-long transition, a journey from mastery into a gathering mystery. The sophisticated knowledge of hydraulic concrete did not disappear with a single fallen aqueduct. Instead, it began a gradual, almost imperceptible simplification as the political and economic world that sustained it transformed. In the surviving Eastern Roman or Byzantine Empire, engineers still understood the value of pozzolanic materials. They used crushed brick dust and certain volcanic soils in their mortars, creating durable binding agents that helped their churches and fortifications stand for ages. Yet the ambition had changed. The scale of imperial infrastructure projects, the vast harbors and continent-spanning aqueducts that demanded the most advanced hydraulic concrete largely ceased. Without the driving need for such specialized, large-volume applications, the precise art of sourcing specific volcanic ashes and executing the hot mix technique began to fade from common practice. The knowledge retreated, preserved in fragments within monastic libraries and the guarded traditions of local mason guilds. It became a set of recipes for good mortar, rather than a systematic science for creating artificial stone. Centuries later, European knights on crusade marched into the Levant and encountered something astonishing. The formidable castles of the Middle East, like crack des Chevaliers, were bound with mortars of legendary strength, far superior to anything they knew at home. These mortars, often using local pozzolanic materials, allowed for taller, thinner walls and more daring architectural feats. When Crusaders returned to Europe, they brought back tales of this superior craft, but they could not replicate its success. They lacked the specific geological ingredients and, more importantly, the deep, embodied understanding of how to prepare and combine them. The result was a patchwork of quality. Examine the mortar in a magnificent Romanesque abbey or a soaring Gothic cathedral. In some places, it is hard and resilient, hinting at a surviving thread of pozzolanic knowledge, perhaps from a local deposit of volcanic ash or crushed brick. In other sections, it is soft and crumbly, having lost that reactive magic, leading to constant repairs and reinforcements over the centuries. The buildings stood as testaments to faith and skill, but their very fabric recorded a quiet decline in material science. This raises a haunting reflection. How much profound knowledge is lost not in a fiery library blaze or a sudden invasion, but in the slow, quiet erosion of daily practice. When a master mason dies without a true apprentice, when a quarry of special ash is abandoned and forgotten, when the economic incentive to build for 1,000 years shrinks to the need to build for 100, the chain of transmission weakens, link by link. The philosophy of permanence itself becomes a luxury, then a myth. By the late medieval period, the full Roman formula for hydraulic concrete was no longer a living technology. It was a ghost in the mortar, a half-remembered legend among builders. The sophisticated synergy of chemistry, heat, and compaction had fractured into disconnected tricks and local traditions. This gradual fade, spanning nearly a millennium, set the stage for a complete rupture. It created a world that would look upon the indestructible works of antiquity, not with understanding, but with sheer wonder, believing them to be the work of giants or a lost magic. The stage was now set for a new age to try and reinvent what had been so patiently forgotten. The Renaissance architect did not see ruins as dead stone, but as living textbooks. When Filippo Brunelleschi stood before the crumbling shell of the Pantheon in the early 15th century, his gaze was not merely artistic. He was a detective at a crime scene, meticulously measuring the curve of the dome, studying the thickness of its walls, and puzzling over the very substance from which it was made. His own revolutionary dome for the Florence Cathedral would be a feat of engineering genius, yet its construction relied on complex brickwork and chains, not the monolithic concrete of his Roman inspiration. Brunelleschi and his peers recognized the superior material in the ancient ruins, but its precise formula remained a locked vault. For the next 400 years, the quest to rediscover Roman concrete became a slow, stumbling journey of misinterpretation and missed clues. Scholars and builders of the era pored over the recovered texts of Vitruvius, but the words were a riddle. They correctly latched onto his mention of a special sand from Pozzolana, but they misunderstood its role. Many believed the secret was a magical additive, a hidden ingredient that transformed ordinary lime into stone. The great architectural theorist Leon Battista Alberti, writing in the mid-15th century, astutely noted that the best mortar came from mixing lime with pozzolana or crushed terracotta. He grasped the what, but the chemical why of the Pozzolanic reaction was a mystery his age could not solve. Without this understanding, attempts at replication were haphazard. Builders might toss some volcanic dirt into their lime mortar, but without the right composition, the right mix proportions, or the hot mixing technique, the results were unpredictable, often weak and nothing like the indestructible fabric of the Colosseum. The trail of rediscovery winds through the 18th century, where a practical breakthrough finally emerged, born from a different kind of fire. Manufacturers began producing what they called natural cements. These were made by burning impure limestone, stone that naturally contained clay. The resulting product, when mixed with water, would set even underwater, mimicking the hydraulic property of Roman concrete. This was a major step, a return to the principle of using a reactive, aluminosilicate material. These natural cements, sometimes marketed as Roman cement, found brilliant application in the harsh marine environments of the burgeoning British Empire. They were used to build iconic lighthouses like the Eddystone Lighthouse and massive seawalls, structures that needed to withstand the relentless ocean. For a few decades, it seemed the ancient wisdom had been recaptured, but the industrial age was accelerating, demanding not just performance, but consistency, speed, and scale. In 1824, an English bricklayer named Joseph Aspdin patented a new material. He called it Portland cement for its resemblance to the prestigious Portland stone when set. Aspdin's process involved artificially creating the conditions of natural cement by carefully proportioning and burning a mixture of limestone and clay at high temperatures, then grinding it into a fine powder. This was the pivotal turn. Portland cement was a marvel of standardization. Every bag was predictable. It gained strength rapidly, allowing faster construction cycles to feed the railways, factories, and cities of the Victorian era. Yet in its chemical pursuit of early strength and uniformity, it quietly abandoned key aspects of the Roman model. The complex, slow-forming calcium aluminosilicate hydrate gel was replaced by a simpler, faster-setting compound. The inherent self-healing potential and the long-term chemical resilience were engineered out in favor of immediate utility. Herein lies the profound historical irony. Just as modern chemistry advanced enough in the late 19th century to finally analyze the atomic structure of ancient Roman samples, the construction industry had already committed wholeheartedly to the new Portland paradigm. The scientific tools to understand the old way arrived precisely as the economic incentives to pursue it vanished. The demand for rapid urban expansion and industrial growth made a material that took centuries to reach its full strength seem not just obsolete but irrational. So we are left with a haunting question from this pivot point in history. Did the Industrial Revolution's insatiable appetite for speed and scale blind us to a fundamentally better, albeit slower, solution? In choosing the predictable powder that built the modern world in decades, did we unknowingly lock ourselves into a cycle of constant repair and replacement, a path away from permanence? The lighthouses of the 19th century, built with the last echo of the Roman principle, still stand guard. Their silent endurance is a testament to the road not taken, a road that now, in our age of environmental consequence, we are being forced to look back upon with new eyes. The most resilient ecosystems often thrive in the harshest environments. Within the alkaline, mineral-soaked pores of ancient Roman concrete, a frontier hypothesis is taking shape, one that suggests the stone was not just chemically reactive, but biologically alive. This sixth component ventures beyond chemistry into the realm of geomicrobiology, exploring the tantalizing possibility that microscopic life played a role in the material's legendary endurance. The concept is called biomineralization, a natural process where living organisms, typically bacteria, influence the formation of minerals. In seashells and coral reefs, we see this clearly: life-building stone. Could a similar, unintentional process have been at work within the harbor walls of Caesarea or the piers of Portus? The environment inside Roman concrete is extreme, highly alkaline, and rich in dissolved calcium and silica. For most life, it would be inhospitable, but certain extremophile bacteria, species adapted to thrive in severe conditions, could find it a suitable home. Researchers theorize that such microbes, perhaps introduced via seawater or within the porous volcanic aggregate, might have metabolized minerals from the surrounding paste. As a byproduct of their life processes, they could have precipitated new, stable crystals of calcium carbonate or silicate, slowly filling voids and microcracks from within. This would not replace the primary pozzolanic reaction, but act as a secondary biological reinforcement over centuries. It is a slow, silent partnership between stone and cell. Modern material scientists are already harnessing this principle deliberately, creating what is known as bioconcrete. These advanced mixes have tiny capsules embedded within them, containing dormant bacteria and a food source like calcium lactate. When a crack forms and water enters, it dissolves the capsules, awakening the bacteria. The microbes then consume their nutrient package and, as part of their metabolism, excrete calcite, a robust form of calcium carbonate, effectively gluing the crack shut within weeks. This is a designed, accelerated version of a process that, in Roman concrete, may have occurred passively and glacially over generations. The search for evidence is like a microscopic archaeological dig. Teams analyzing ancient concrete cores, particularly from marine sites, are not just looking at minerals, they are searching for subtle biosignatures, fossilized remnants of bacterial colonies or chemical traces that only life could leave behind. Finding conclusive proof is challenging, as 2 millennia can erase delicate organic evidence. Yet, the very structure of the material offers clues. The way certain minerals are deposited in some pore spaces, in layered, botryoidal forms that resemble microbial mats found in natural hot springs, hints at a biological architect. This idea reframes our understanding of the material in a profound way. We have moved from seeing it as a sophisticated chemical artifact to a potential biogeological hybrid. If microbes were active participants, then the concrete was not a static monument, but a dynamic, low-level ecosystem. Its durability was not merely engineered, it was, in a sense, cultivated. This leads to a reflective question that straddles science and philosophy. Could the ultimate, forgotten ingredient in Roman concrete be time itself, facilitated by life? Their formula may have created the perfect mineral-rich substrate, an accidental garden where certain bacteria could slowly, patiently weave a stronger stone. It suggests a model of durability that is not about resisting nature, but about selectively collaborating with it, enlisting even the smallest forms of life in the work of preservation. This biological dimension, still an emerging theory, adds breathtaking complexity to the mystery. It implies that the Romans, through empirical mastery, may have stumbled upon a principle modern science is only now learning to codify, that the most enduring structures might be those that are, in a subtle way, alive. The volcanic ash from Pozzolana could not build the baths of Diocletian alone. That single structure, a sprawling complex of pools, libraries, and gymnasiums, consumed more material than most modern stadiums. Its completion was not just a triumph of architecture, but a staggering feat of logistics, a silent symphony of extraction, transport, and labor conducted across the entire Italian peninsula. The concrete formula was the star, but it performed on a stage built by the Roman economic machine. This system transformed a local geological advantage into an empire-wide capability. At the heart of this operation were the quarries and kilns, industrial landscapes humming with organized activity. Archaeological surveys of Pozzolana pits near Rome show not random digging, but methodical extraction, following the richest seams of reactive ash. These sites were connected by a web of purpose-built roads and, most crucially, rivers. The Tiber River became a liquid conveyor belt, its currents carrying barges laden with the precious gray powder from inland deposits directly to the growing capital. For maritime concrete, the supply chain was even more direct. Ships would load volcanic ash at ports like Puteoli, near the source, and sail it to harbors under construction hundreds of miles away. This network meant a builder in Carthage or Alexandria could, if the project demanded it, access the finest Pozzolana from Italy. Yet the system's brilliance lay in its flexibility. While the empire could move specialized materials across great distances, its engineers were not slavishly dependent on them. As we have seen, they constantly adapted, using local volcanic soils in Gaul or crushed brick in Britain. The imperial infrastructure provided the option for uniformity in flagship projects, while a decentralized principle of local adaptation served everyday construction. This balance was made possible by the Pax Romana, the Roman peace. Secure roads, policed sea lanes, and a unified economic zone allowed for the predictable movement of heavy, low-value bulk materials like sand, stone, and ash. A merchant could contract to deliver 1,000 tons of tuff from a quarry to a port with reasonable assurance his shipment would not be plundered. This stability lowered the transactional cost of grand ambition. The human engine of this system was a stratified, highly specialized workforce. At the top were the architects and engineers, often freemen with advanced education. Then came the skilled craftsmen of the collegia, the guilds, who understood the mixes and supervised the pouring. The bulk of the labor force consisted of both paid freemen and enslaved individuals, each assigned specific, repetitive tasks. Some crews worked the kilns, maintaining the precise heat for days to produce quicklime. Others operated the quarries, or manned the barges, or served on the mixing teams at the construction site itself. This division of labor turned a complex chemical process into a repeatable, scalable assembly line. Evidence of this organizational mind is literally stamped into the material. Bricks and tiles found embedded in Roman concrete often bear the mark of their manufacturer, a stamp indicating the brickyard owner, the foreman, or sometimes even the reigning emperor. This was not vanity. It was a system of accountability and quality control. If a batch of bricks failed, the source could be traced. These stamps allow archaeologists today to map the supply routes of a single building, revealing that materials might come from multiple, competing suppliers, all coordinated to meet a relentless construction schedule. So we must ask, was the ultimate secret ingredient of Roman concrete the Roman state itself? The formula was not just a list of components. It was a living process sustained by imperial-scale logistics, secure transport, managed labor, and quality assurance. The knowledge of how to mix the ash and lime was vital, but it was useless without the system that delivered the ash to the mixing trough. When that vast, interconnected network began to fray, as roads fell into disrepair, long-distance trade contracted, and the centralized authority that managed mega projects dissolved, the technology did not simply vanish. It became logistically impossible. The recipe remained, but the kitchen, the supply chain, and the organized staff needed to prepare it slowly faded away, leaving behind only the enduring meal. A flawless material would have built an empire without a single crack. Yet walk through the ruins of the Roman Forum today, and you will find concrete surfaces pitted and scarred, sections where the aggregate stands proud like bones after the flesh has eroded. This is not a betrayal of the formula, but a vital clue to its true nature. Roman concrete was not a magical, invincible substance. It was a brilliant technology with specific strengths and equally specific vulnerabilities, engineered for a Mediterranean world. Its greatest weakness was a direct consequence of its greatest strength. Designed to excel under massive, crushing weight, it possessed little inherent resistance to bending or pulling forces, what engineers call tensile strength. This is why you never find a long, slender Roman concrete beam spanning a great distance on its own. For that, they turned to stone lintels or, more ingeniously, transformed the problem into one of compression through the arch and the vault. A concrete arch channels forces beautifully into compression along its curve, but ask that same material to act as a simple, horizontal bridge, and it would fail. This fundamental limitation dictated Roman architecture, shaping its heavy, grounded aesthetic. Beyond this structural rule, the material faced environmental enemies its creators could not have foreseen. In the damp, cold northern frontiers of Britannia or Germania, where freeze-thaw cycles are relentless, Roman concrete shows a different kind of wear. Water would seep into its pores and then freeze, expanding with enough force to slowly spall and crumble the surface over centuries. This weathering reveals a concrete optimized for the stable, dry climate of Italy, not the harsher rhythms of the north. Even in its heartland, certain applications proved challenging. The acidic environment of early sewer systems, for instance, could gradually degrade the alkaline binder over time. And the material's incredible durability came at a physical cost: weight. Roman concrete was dense and heavy, requiring enormous, deep foundations. This made it impractical for building on soft or unstable ground without extensive and costly preparatory work. Perhaps the most significant limitation from a modern perspective was time itself. The slow, continuous curing that granted its longevity was a luxury of an era without quarterly earnings reports. The Pozzolanic reaction that strengthened concrete for centuries meant it also gained its usable strength over weeks or months, not days. A modern high-rise project, with its precise scheduling and financial pressures, simply could not wait for a material to reach its optimal state over a human lifetime. It needed a material that could bear the next floor's weight in a matter of weeks, so we must look with clear eyes at a place like the markets of Trajan. While its concrete vaults stand magnificently, some exterior surfaces exposed to 2 millennia of rain, pollution, and temperature swings show clear degradation. Contrast this with the pristine, sheltered interior of the Pantheon's dome, protected from direct weathering. The difference is not a flaw in the recipe, but a testament to its context-dependent nature. This honest assessment leads to a crucial reflection. Are we idealizing an ancient technology by only gazing upon its surviving masterpieces? To understand the true scope of its genius, we must also study its fractures and its failures. These limitations are not marks of inferiority. They are the boundaries of its design, the edges of the problem it was meant to solve. Recognizing where the material struggled helps us see its triumphs not as mysterious magic, but as brilliant, focused engineering. It was the right tool for a specific set of jobs within a particular civilization and climate. This clear-eyed view frees us from mere nostalgia and allows a more powerful question to emerge. Instead of asking how to blindly copy an ancient recipe, we can ask a more sophisticated one. How do we capture its principles of resilience and longevity while overcoming its historic limitations for our own world? A Roman citizen walking through the newly paved Forum did not see a construction project. He witnessed the solidification of destiny. The concrete vaults and soaring domes rising around him were not merely functional spaces. They were the physical argument of an empire built to outlast time itself. This drive for permanence had a name, eternitas, a cultural and religious ideal that permeated Roman statecraft. The concrete formula was not just an engineering solution, it was the ultimate tool for this philosophical mission, a way to translate imperial ambition into unyielding stone. Where modern builders might calculate cost per square foot, Roman patrons and engineers calculated legacy per century. This cultural imperative justified everything the concrete process demanded. the vast slave and freeman labor to mine the ash, the days of burning lime, the slow, careful curing that locked away capital and resources for years before a return was seen. It was a luxury of conviction, a belief that the most important return on investment was a name remembered 1,000 years hence. Classicists note how Roman religion was deeply intertwined with the state, and the permanence of the state's monuments reinforced the perceived favor of the gods. To build in ephemeral materials was to doubt Rome's eternal destiny. Historiography, the writing of history, further cemented this. Leaders understood their deeds would be judged by the ruins they left behind, quite literally. The historian Tacitus wrote of the city being transformed from brick to marble under Augustus, a metaphor for moving from the temporary to the eternal. Concrete was the unseen engine of that transformation, the material that made marble cladding possible on a colossal scale. This long-term mindset fostered a unique environment for innovation. A master mason could spend a lifetime perfecting a mixed proportion, knowing his grandson would see the final result of his experiments in a dome that would stand for ages. This was iterative, generational science, patient and cumulative, utterly disconnected from the quarterly profit cycles that dictate modern material development. The proof is etched in stone, not just in the structures but on them. Inscriptions and dedications were carved with the certainty that the wall they adorned would last as long as the message. The Res Gesti Divi Augusti, the monumental autobiography of Rome's first emperor, lists his building projects as a core pillar of his legacy, alongside military victories. He rebuilt temples, constructed aqueducts, and boasted of finding a city of brick and leaving one of marble, a statement underpinned by the revolutionary concrete that made such grandeur possible. The mausoleum of Augustus, his own intended resting place, was a massive concentric cylinder of concrete and earth, a structure meant to declare his memory permanent. This cultural engine raises a reflective and perhaps uncomfortable question for our own time. Can a society that primarily values speed, efficiency, and disposability ever build things that are meant to last 1,000 years? Our economic models reward rapid turnover and planned obsolescence. Our public discourse rarely speaks of a building's performance in the year 3000. The lost formula, then, may be as much a casualty of a shifted mindset as of forgotten logistics. We misplaced not just the recipe for the mix, but the recipe for the ambition that demanded such a mix in the first place. The concrete was the how, eternitas was the why. Without that powerful, unifying why, the intricate how could not survive the fall of the world that cherished it. This philosophical loss sets the stage for the final, practical unraveling, the moment when the last master of the old craft took his unrecorded secrets to his grave, leaving a new world to puzzle over stones it could no longer make. A laboratory glove dips into a slurry of gray powder, not a modern cement, but a precise replica of a 2,000-year-old Roman mix. In climate-controlled chambers, sensors monitor blocks of this ancient formula as they are subjected to cycles of freezing, thawing, and immersion in synthetic seawater. This is the cutting edge of archaeomaterial science, where the goal is no longer just to understand history, but to rebuild it for our own time. Teams at institutions like the University of California, Berkeley, MIT, and research centers in Europe and Asia have achieved a profound success. They have cracked the chemical code. We now know with molecular precision why the Roman concrete worked. The complex nanostructure of the calcium aluminosilicate hydrate gel, the role of the hot lime clasts, the self-healing mechanisms, these are no longer mysteries. The scientific understanding is clear and replicable in a controlled lab environment. The real test, however, lies outside the laboratory door in the messy, regulated, and cost-driven world of modern construction. Here, the path from brilliant insight to common building material is fraught with obstacles that have little to do with chemistry. The first major hurdle is the raw material itself. The Roman Empire was built on the specific geology of central Italy. Their Pozzolana came from consistent, massive volcanic deposits. For a global construction industry, sourcing a uniform, natural pozzolan of that quality and reactivity is a logistical and geological nightmare. Not every country has a conveniently located volcano, and the composition of volcanic ash can vary dramatically from one eruption to the next, even from one side of a hill to the other. Modern industry demands predictability. A builder in Dubai or Denver needs to know that bag number 1 million will perform exactly like bag number 1. This has led researchers and pioneering companies to look at industrial byproducts as modern pozzolans, primarily fly ash from coal plants and slag from steel production. These materials are abundant, consistent, and their use is a form of brilliant recycling. Blending them with Portland cement creates a concrete that is more durable and has a much lower carbon footprint, directly applying the Roman principle of using a reactive silica alumina material. Projects like the One World Trade Center Foundation used massive amounts of slag cement, not for historical accuracy, but for superior performance in a corrosive marine environment. This hybrid approach, using modern cement as a base but replacing large portions of it with pozzolanic supplements, is perhaps the most viable commercial path forward. It offers a bridge between ancient wisdom and contemporary need. Yet, even this hybrid faces the rigid wall of modern building codes. Our entire regulatory framework for structural concrete is built around one sacred number, the 28-day compressive strength. A material's fitness for purpose is judged by a test performed less than a month after it is poured. Roman-style concrete, with its slow, continuous strength gain from the ongoing pozzolanic reaction, is at a severe disadvantage in this system. It might have a lower strength at 28 days, even as its long-term potential far exceeds that of conventional mixes. Convincing engineers, insurers, and code officials to approve a material whose primary strength manifests over decades, not weeks, is a monumental challenge of shifting mindset, not just mix design. This makes widespread use in fast-paced commercial projects, like skyscrapers or highway bridges, currently impractical. The economic model cannot accommodate the weight. Where this ancient knowledge is finding a true home is in niches where its unique properties are irreplaceable. Consider the meticulous restoration of historic structures like the San Antonio missions or ancient monuments in Rome itself. Here, conservators use mortars based on Roman recipes, ensuring new repairs are chemically and physically compatible with the old fabric. The new mortar will age and weather at the same rate, preventing damage caused by harder, less permeable modern materials. Another promising arena is marine construction. Companies are developing and testing specialized concrete mixes, often called duckrete or similar branded names, for use in submerged elements like seawalls, tidal energy platforms, or artificial reefs. In these applications where saltwater corrosion is the primary enemy and construction pace is less frantic, the Roman formula's virtues shine. A seawall that self-heals microcracks and grows stronger in seawater could last for centuries, eliminating the cycle of costly, disruptive repairs. So we stand at a fascinating crossroads. The science is solved, the recipe is known. The question is no longer can we make it, but will we choose to build a world that values it? The future of concrete may not be a wholesale return to the Roman mix, but a sophisticated fusion. Imagine a material engineered at the nanoscale, with encapsulated healing agents inspired by the lime clasts, using optimized industrial pozzolans, and perhaps even cultivated bacteria, all designed to pass a modern 28-day test while possessing the ancient capacity for centuries of silent, resilient service. The greatest challenge is no longer in the chemistry lab, but in our economic calculations and our cultural imagination. Can we learn to value the 100-year strength as much as the 28-day strength? The answer will be written not in research papers, but in the next generation of harbors, foundations, and perhaps even monuments we dare to begin. The blueprint for the future of building may not be drawn on paper, but encoded in the slow chemistry of the past. We stand on the brink of a materials revolution that does not seek to merely replicate Roman concrete, but to understand and transcend its principles, giving rise to an entirely new generation of construction substances born from the marriage of ancient insight and cutting-edge science. This emerging field is called geomimicry, the deliberate imitation of geological processes to create human-made materials. Instead of forcing rocks to melt in infernal kilns, researchers are learning to coax them to grow at ambient temperatures, mimicking the patient, low-energy ways of the Earth itself. Here, the guiding stars are the very virtues we have traced: slow curing, inherent self-healing, and radical reductions in embodied energy. The reign of 19th-century Portland cement is being challenged not by nostalgia, but by superior performance inspired by a 2,000-year-old model. At the forefront are alkali-activated materials, often called geopolymers. Think of them as a sophisticated, engineered cousin to the Roman mix. Instead of using Portland cement as the glue, these materials activate industrial byproducts like fly ash or slag with an alkaline solution, sparking a geopolymerization reaction. This forms a three-dimensional aluminosilicate network, a molecular structure conceptually similar to the durable gel in Roman concrete, but tailored and accelerated. The result is a stone-like material that can be stronger, more resistant to heat and chemicals, and crucially, can cut associated carbon emissions by up to 80% or more. Another promising path is calcium sulfoluminate cement, which cures quickly with much less heat required in its production, again aligning with the Roman pursuit of lower thermal ambition. These are not lab curiosities. Pilot projects are already employing them in everything from railway sleepers to building panels, proving their viability in the real world. The most visionary frontier, however, moves beyond even mixing powders. It involves growing buildings. In laboratories, scientists are pioneering biocementation, using bacteria that naturally produce urease, an enzyme. When these microbes are introduced to a sand mixture with a calcium nutrient, they trigger the precipitation of calcite, effectively gluing the sand grains together into a solid sandstone. This process happens at room temperature, requires no fossil fuels, and the resulting material can be designed to repair itself, as new bacteria can be embedded to activate when cracks form. Separately, the technique of electrochemical mineral accretion, where a low-voltage current is passed through a steel mesh in seawater, causes dissolved minerals to crystallize onto the frame, building up a solid, coral-like structure over time. These approaches represent a paradigm shift from construction to cultivation, where a structure matures and strengthens in place. This points toward a future where adaptability and locality are paramount. Imagine construction sites not receiving uniform bags of gray powder from a distant factory, but instead using regionally sourced reactive materials, crushed volcanic rock from a local quarry, pulverized recycled glass from a city's waste stream, or slag from a nearby steel plant. Three-dimensional printers could then layer these customized geomimetic mixes into complex, efficient forms impossible with traditional casting, all while software calculates the optimal gradation and density, much like the Pantheon's dome, but with digital precision. The structure would then be left to cure not for 28 days, but to mature for decades, its strength and resilience increasing as its internal chemical conversations continue, a built-in legacy. Perhaps the most profound potential lies in turning a climate villain into a climate solution: carbon-negative cement. Some of these new materials, particularly certain geopolymers, are not just low carbon. They can actively absorb carbon dioxide from the atmosphere as they age, through a process similar to the long-term carbonation that occurs in Roman concrete. A building could thus become a carbon sink, its very fabric helping to clean the air over its centuries-long life, fulfilling the ultimate promise of sustainability, giving back more than it took. So we return to our central mystery with a new lens. The silent, enduring stones of Rome were not an end point. They were a signpost. Could the ultimate legacy of those ancient engineers be the catalyst that finally liberates us from the limitations of our own 19th century invention? The answer is being written in laboratories and pilot projects today. The ancient past, it seems, was not merely a record of what we lost, but a persistent whisper of what we might still become, offering a blueprint not for a forgotten empire, but for a sustainable, resilient future. A tiny drill bit whirs against stone that has stood silent for 1900 years. The paradox is as stark as the sound. To unlock the secret of its immortality, we must first inflict a wound. This is the profound ethical dilemma at the heart of modern archaeomaterial science, a field caught between the imperative to understand and the sacred duty to preserve. Every core sample extracted from the Pantheon's dome or a harbor block at Caesarea is an act of controlled damage, a permanent alteration to a finite cultural treasure. Conservators speak of a guiding principle, minimal intervention, where any physical contact with a historic fabric must be justified by a greater good and executed with surgical precision. The question is never simply, can we take a sample? It is, must we, and if so, where is the least harmful place? The answer often lies in the scars history has already made. Researchers meticulously seek out areas of previous damage, hidden joints or sections already slated for necessary stabilization work. Underwater sites, like the submerged harbor works, offer a unique ethical reprieve. Here, the concrete has been removed from its original architectural context by nature itself, allowing for more extensive sampling with less conflict, turning the seafloor into an open-air laboratory of unparalleled value. The scientific community has responded to this ethical challenge with a surge of ingenuity, developing non-invasive techniques that peer into stone without breaking its skin. Neutron scattering, for instance, can map the internal structure and moisture content of thick walls by measuring how subatomic particles pass through them. Muon tomography uses cosmic rays to create X-ray-like images of dense structures, revealing hidden chambers or voids. Portable X-ray fluorescence devices allow an archaeologist to stand before a wall and, with a handheld scanner, determine its elemental composition in minutes, all without a single scratch. A compelling example of this careful approach unfolded within the Pantheon itself. Faced with questions about the dome's internal composition, researchers did not immediately drill. Instead, they used a borescope, a slender endoscopic camera, inserted into existing cracks or tiny, pre-existing openings. This allowed them to visually inspect the layered aggregate inside the wall, confirming the vertical gradation from heavy stone to light pumice, all while leaving the monument virtually untouched. These methods are governed by strict international protocols and often require collaborative approvals from multiple governmental and cultural heritage bodies. The process is slow, deliberate, and transparent, ensuring that the pursuit of knowledge does not become a reckless plunder of the past. This framework forces a necessary reflection. How do we weigh the potential benefit to future generations against the permanent cost to a legacy we hold in trust? The responsible study of Roman concrete is not a race. It is a careful conversation with the past, where every question asked must be worthy of the slight, irreparable mark it may leave behind. In this ethical balance, the ultimate goal shifts from mere acquisition of data to a deeper form of stewardship, ensuring that the silent lessons of these stones can be heard for centuries to come, by ears not yet born to a world still being built. 26 separate pieces of a puzzle now lie before us. Each one, from the volcanic ash to the philosophy of Eternitas, is a vital clue, yet none alone reveals the complete picture. The true secret of Roman concrete was not a single lost ingredient, but the masterful orchestration of every step, from the heart of the volcano to the hands of the builder and the patience of centuries. It was a grand, holistic system where chemistry, physics, craftsmanship, and culture converged into a single, unified theory of permanence. Think of it not as a recipe, but as a symphony. The volcanic Pozzolana provided the reactive melody, rich in silica and alumina. The hot lime was the volatile, energetic rhythm section, releasing heat that optimized the initial cure. The seawater or mixing water was the conductor, initiating and sustaining the slow chemical performance. The jagged, graded aggregate formed the physical chorus, a dense internal skeleton. The meticulous tamping and layered placement were the precise notations on the sheet music, ensuring no weak notes. And the overarching cultural drive for eternity was the composer's ambition. The reason the symphony was written to be performed not for a season, but for all time. Break any single link in this chain, and the magic dissipates. Use the perfect ash, but mix it cold and slaked, and you lose the thermal optimization that creates a tougher nanostructure. Achieve the ideal chemistry, but rush the placement or use smooth aggregate, and you introduce weak planes and poor bonding. Design a self-healing matrix, but reinforce it with steel, and you implant the seed of its own corrosion-driven destruction. Even with the flawless material and technique, without the cultural and economic patience to let it cure for months or years before bearing full load, the long-term benefit is squandered for short-term gain. Experts now describe Roman concrete not as a primitive building material, but as a designed composite geologic material. This is a profound shift in perspective. They did not simply make a substitute for stone, they engineered an artificial rock with a built-in evolutionary path. It was designed from the outset to partner with time and environment, to use exposure not as a degrading force, but as a curing agent. The seawater that crystallizes harmful salts in our concrete instead grew beneficial minerals in theirs. The tiny cracks we patch from the outside, their material could heal from within. This was engineering with a different horizon line. Visualize a flowchart that begins with a specific volcanic eruption, creating a unique glassy ash. That ash is mined and transported via a secure imperial network to a construction site, where it meets lime burned in a standardized kiln. The two are combined in a hot mix, triggering an exothermic reaction, then blended with carefully selected local aggregate. The mixture is placed with deliberate craftsmanship into a formwork shaped for pure compression without a speck of steel. It is then left not just to dry, but to begin a centuries-long conversation with the elements, rain, air, and in the case of harbors, the sea itself. Each step feeds the next, a cascade of cause and effect culminating in a structure that grows denser and more resilient long after its creators are gone. So we must ask the culminating question. In our modern pursuit of optimizing each individual variable for maximum speed and profit, have we lost the wisdom of the synergistic system? The Roman model suggests that ultimate resilience cannot be found in a single, isolated breakthrough. It emerges from the integrated complexity of many interdependent parts, from the geology of the quarry to the patience of the culture. The concrete did not succeed in spite of its slow curing, its variable natural ingredients, or its lack of metal reinforcement. It succeeded precisely because of those things. This grand synthesis is not the end of the story, but the key that unlocks its final, most urgent meaning. For if we now understand the symphony in its entirety, what music might we choose to compose for our own uncertain future? The silent challenge of those ancient stones is no longer a mystery but a mirror. As we return from the depths of history, the message in the mortar is unmistakable. The lost formulae of Roman concrete are not a relic to be catalogued and forgotten. They are a masterclass in sustainable, resilient design, a 2,000-year-old blueprint that speaks with startling clarity to the environmental and infrastructural crises we face today. We have traced the path from volcano to vault, and the ultimate revelation is this: the secret was never a single magic powder hidden in a scroll. It was a profound, holistic integration, a way of thinking about construction that wove together locally adapted geology, patient, empirical craftsmanship, and a cultural philosophy that measured success in centuries, not fiscal quarters. The key takeaways are not just chemical but philosophical. They champion long-term thinking over short-term gain, demonstrating that a society's most enduring legacy is built on patience. They reveal the immense power of leveraging natural chemical processes, of partnering with the environment rather than perpetually defending against it. And they underscore a radical principle of material design, that true strength emerges from synergy, from creating systems where every component, even perceived imperfections like lime clasts or variable ash, contributes to a greater, more durable whole. This exploration, then, must become more than an intellectual journey. It is a call to action. For the materials scientist in the lab, it is an invitation to look beyond optimizing for 28-day strength and to design for 200-year resilience. For the engineer on the construction site, it is a challenge to reconsider local materials and slower, more deliberate methods. For policymakers shaping our built environment, it is a plea to write codes and create incentives that reward longevity and low carbon footprints, valuing the century-long performance of a harbor wall as much as its initial cost. The Romans left their challenge not in words but in enduring stone, in a dome that still opens to the sky and harbors that still break the sea. Their silent question hangs in the air of every crumbling modern bridge and every carbon-intensive rebuild. Can we learn to build a world meant to last? The ingredients for that future are all around us, in the industrial byproducts we discard, in the local geology we ignore, and most of all, in the shift of mindset we must dare to make. The ancient tech is not a recipe to copy, but a principle to rediscover, a reminder that the most advanced path forward might just begin with looking thoughtfully